So we're seeing the same slide that we left off, or that was near the end of our last video. The take-home message at that point was the rate of the forward has to be equal to the rate of the reverse reaction to be at equilibrium. So we took the rate law of the forward reaction and set it equal to the rate law of the reverse reaction, and that's what we got. I said we're going to do some further manipulation of this in the next video. Ta-da! We're here now. So in knowing that this is true, some people who are real bright did a lot of experiments, starting with different concentrations of NO2 and different concentrations of N2O4. These are initial concentrations, so you start with all kinds of different concentrations. And at equilibrium, they established a steady state concentration. Remember, the reaction has not ceased. It's just that the concentration is staying the same because the rate of the forward is equal to the rate of the reverse. It's kind of a big deal if you haven't figured that out yet. So when they did this, they started manipulating these values that they got. Said, what if I put concentration of this over concentration of that? There's a bunch of values. Okay, great. So what? What if I put concentration of this squared over concentration of that? Ooh, that seems important. When you put NO2 squared over N2O4, you get a value that is a constant. So if I rearrange my equation down here, I've written it already rearranged, but all I'm doing is dividing both sides by N2O4 and moving my reverse rate constant to the other side to divide over there. So forward over reverse, the rate constant of the forward divided by the rate constant of the reverse is equal to NO2 squared over N2O4. The concentration of NO2 squared over N2O4. Sure. So when you do that, that's a rate constant over a rate constant. Did you hear my repeated word there? That's a constant. It's a rate constant over a rate constant. It's a constant. And that constant we will call KEQ. So I hinted at it in the last video. That KEQ stands for equilibrium constant. The sucky thing that is unfortunately a little bit of a big deal. Rate constants are lowercase k. Equilibrium constants are big K. Always, always, always big K. Big K is a unitless number. This would be molarity squared over molarity. No, that turns out to molarity. We don't give KEQ units, actually. Regardless of whether it's molarity squared over this, over that. No, we leave KEQ as unitless. So, let's talk about what this KEQ means and what do you do with it. Yeah, it's a constant. The KEQ of this particular reaction is 4.63 times 10 to the negative third at 25 Celsius. It should be noted that that table of data is at 25 Celsius. Temperature is something that will change rate constant. But did my concentrations, when I changed different concentrations here, did it change my equilibrium constant? I think I said rate constant a second ago. That was an accident. Did it change my equilibrium constant? No. There's like little tiny differences in decimals over here, but no. Starting with any kind of concentration over here, whether it's none of one thing and lots of the other, some of both, some of both, some of both, some of one and none of the other, it doesn't matter. You're going to establish equilibrium, and at 25, again, temperature is important for equilibrium constants. At 25, this reaction will always have this equilibrium constant. Okay. So what are equilibrium constants? How do we write them? Do we always have to go through, write the rate law of the forward, write the rate law of the reverse, and set them equal to each other? No. In general, they look like this. Given our favorite generic reaction here, we would write a KEQ that's C raised to the C power, D raised to the D power, multiplied together, divided by A raised to the A, B raised to the B, multiplied together. The shortcut way that I always say that is products over reactants raised to their coefficients. So it's the concentration of a product raised to its coefficient, multiplied by the concentration of the next product raised to its coefficient, divided by reactants raised to their coefficients, multiplied together. Yeah. What does a KEQ mean? If KEQ is greater than 1, aka KEQ is a big number, that actually tells you something about the equilibrium process. So remember I said equilibrium means you have some products and some reactants left over. Absolutely, at the end of the reaction, you've got some of both. The reaction does not go to completion. If your KEQ is greater than 1, aka a big number, that means that you have more products than you have reactants. So that's because your numerator is a much bigger value than your denominator, that your KEQ is so large. So we will say that equilibrium favors products. We also use the terminology that equilibrium lies to the right, meaning there's more products than there are reactants in that reaction. Conversely, if KEQ is small, less than 1, we would say it favors reactants. That's because the numerator is smaller than the denominator, making this a less than 1 kind of number. It favors reactants, and that also means it lies to the left. So this particular reaction is 10 to the negative 3. That's definitely less than 1 overall. So this reaction favors, waiting on you. This reaction favors reactants because it's less than 1. Okay. So that was this given reaction, but equilibrium reactions can be written in the forward direction or the reverse direction. What if I wrote the same reaction but in reverse? What would the KEQ of that thing be? Well, that would be products, concentration of products, into O4, raised to their coefficients, raised to the first power, divided by the concentration of reactants, raised to their coefficients. That would be the second power. That's my KEQ expression, and I will try to be very consistent in my wording. That's a KEQ expression. So that's all well and good. I wrote the expression, but what's the KEQ value? Well, how do I find out what number that's equal to? Well, how does this KEQ expression relate to that KEQ expression? It's the same, but flipped upside down, right? The numerator and denominator have swapped places. What that really means is take this number and flip it upside down. So 1 over 4.63 times 10 to the negative 3 equals the KEQ of this thing. And I don't have my calculator handy right now, but I've got it all on the PowerPoint. So let's see. 216. Yep. So we said this one was less than 1, so it favors reactants. This one is absolutely greater than 1, so it favors products. The cool news about that is it absolutely makes sense because it's the same reaction. Favoring reactants means you've got more N2O4 in solution. Favoring products means you've got more N2O4 in solution. That better be, it's not solution, it's in the gas, but that better be the truth. When the reaction is reversible, when the equation for a reversible equation is written in reverse, the equilibrium, boy, I'm tripping over all my words. The equilibrium constant is the reciprocal of the original. Yep. Okay, cool. Let's do some more stuff. At what time is equilibrium reached? I give you so many answers, but I'm not going to give you this answer. We'll make you answer that question on your own. Not going to answer it whatsoever. You're welcome. Which species are reactants and which species are products? Well, this blue trace is decreasing, so that's a reactant. That means A is a reactant. This red trace is decreasing. That means C is a reactant. The green and purple are increasing. That means D and B are products. Okay, cool. What's next? What's the overall chemical reaction? This one takes a little more manipulation. So, let's see. If we say we know A plus C yields D plus B. The question is it 1A plus 1C yields 1D plus 1B? Probably not. And the reason I can already say probably not is if we made one purple thing for every one green thing, they would increase at the same slope. They don't. This one increases slowly while that one increases dramatically. So there are going to be some coefficients in front of my species here. How do I figure out what those coefficients are? I'm going to say, what's my starting concentration? Because my concentration's on the y-axis. My starting concentration of A is 3 molar. My starting concentration of C is 2 molar. Starting concentration of D and B, both of those start at 0. My ending concentration of, or nope, I shouldn't say ending. I'm not editing it out though. My equilibrium concentration of A. That means over here where it's flatlined, it's at 2.5. C, over here where it's flatlined, that's 1. Purple one, that's B, that's at 0.5. And green one, that's at 1.5. So my concentrations where I started and where I reached equilibrium, that's what's happened. The change that happened in the middle, we need to figure out how much was lost. I lost 0.5, I lost 1, I gained 1.5, and I gained 0.5. That gets squishy and illegible, I know, but lost 0.5, lost 1, gained 1.5, gained 0.5. What do I do with that information? Well, I need to put whole number coefficients out front to make sure that I'm losing things and gaining things in the right ratios. So I find the least common, I want to call it the least common multiple, but I'm pretty sure that's the wrong terminology. But I find what each of those change numbers are divisible by to make them into whole numbers. So I divide each of those by 0.5 to make it into a whole number. So that means 1A, 2C, 3D, and 1B. The good news about this being on video is you can watch this again. I know sometimes students get real confused when I do that kind of thing. But that leads me to the overall reaction. A plus 2C yields 3D plus B. I need whole number coefficients. You can't leave them as fractional coefficients. Okay, we're almost done. What's the equilibrium constant expression? What's the value of the equilibrium constant? Okay, I'm gonna write my expression and my value down below because I write real big. So expression, that means in variable terms, what's the equilibrium, KEQ, equilibrium constant expression? I'm gonna use my equation that I just came up with. So it's products raised to their coefficients multiplied together, that's D cubed times B, divided by reactants raised to their coefficients multiplied together. So that's A times C squared. Okay. The value of the equilibrium constant means plug in the concentrations of each of the components at equilibrium and solve. So that's D is 1.5 cubed. I'm getting it from that right there. Slash, I'm getting it from this right here, that concentration over there when it's steady. Oh, nope, that's the wrong color. The green one. Oops, sorry. 1.5 cubed times 0.5 divided by A is 2.5 at equilibrium, and C is 1 squared. So I do that with a little calculator. Hold, please. If I did my math right, that's 0.675. That's my KEQ. It's a unitless number. Chemists are all about the units, but it's a unitless number. It's less than 1, so that means equilibrium favors the... That one's for you. Okay, moving on. For gases, partial pressure is the preferred unit of the equilibrium expression. Okay, cool. We got a gas, we got a gas, we got a gas. We could write a KEQ, and the KEQ would be H cubed times N2 divided by NH3 squared. That's the KEQ that we've been talking about, but that's often called the KC, where C stands for concentration. So concentrations are what I have plugged into the KEQ expression. Pressure is KP. What? Yep. KP is what we call it when we plug in partial pressure values instead of concentration values. So because each of the three of these are gases, it means the partial pressure of hydrogen gas cubed times the partial pressure of nitrogen gas raised to the first power divided by the partial pressure of NH3 ammonia gas squared. That's the equilibrium expression using partial pressure. So KC is the equilibrium constant filling in concentration. KP is the equilibrium constant filling in partial pressures. Yep. Here it is all tidy and typed out. Yeah. I should have pointed out, this says pressure is an intensive property. What does that mean? Pressure is an intensive property. That means it's independent of the amount that you have. Intensive and extensive are two of those terms that might creep up from time to time. Extensive depends on the amount that you have. Intensive does not. Okay. Solid concentrations are constant and are excluded from the equilibrium expression. What that means is, when I have a reaction that has a solid in it, I do not write it in my equilibrium expression whatsoever. Because as long as some solid is present, the concentration of that solid is not a thing. Like, we don't talk about concentration of solids. We talk about concentrations of liquids and concentrations of gases, but we don't talk about concentrations of solids. So at the end of this reaction, or after equilibrium has been established, we still have some solid present. The concentration of that solid does not matter whatsoever. It's not a thing. So, knowing that K is products of reactants, our Kc, meaning using concentration values, would be CO squared, concentration of CO squared, divided by concentration of CO2. The end. No carbon solid in there whatsoever. You could also write Kp for this because both of my products are gases. So I could write Kp of this reaction as partial pressure of CO squared over partial pressure of CO2. Done. Easy enough. Products of reactants raise their coefficients multiplied together. You should write the equilibrium constant expression for this thing as one of the questions, and I'm going to be done. The end.